EDX Mechanics 1, Work Energy and Power 2, Power. Power, Force and Velocity. We know that power is the rate at which work is done. So power equals work done by the force divided by time taken. However, we also know that work done is force times distance. So the formula can be written as force times distance over time taken, or power equals force times velocity. It's worth pointing out that power is a scalar quantity, and therefore you'd normally be dealing with the speed of the motion rather than the velocity. So P equals F times V. But what do we know about P, F and V? Usually we would be considering the power developed by an engine, which would be producing a driving force, often referred to as attractive force, Ft. V is the velocity of the vehicle, which might be constant or maximum or just an instantaneous value, but it will not be negative, and therefore we can usually consider the speed of the vehicle instead. So if P equals Fv, this leads to an alternative definition of the watt, which is more often used. 1 watt is the power produced by a force of 1 Newton acting on a body moving at 1 meter per second. So in this example, we need to calculate the power developed by a car's engine, which produces a driving force of 1000 newtons when travelling at a constant speed of 45 kilometers per hour. So the first thing we're going to do is to convert the 45 kilometers per hour. So I'm going to times it by 1000 to make sure we're working in meters, and divide by 3600 to make sure we're working in meters per second, which gives us a value of 12.5 meters per second for the speed of the car. We now want to look at the power. So the power of the engine, as we've seen before, is the driving force times the speed. So the driving force is 1000 newtons, and the speed we've just calculated is 12.5 meters per second, which gives us a power of 12,500 watts, or if you prefer, 12.5 kilowatts of power from the engine. As we can see the calculations there. In this new problem, we have a car of mass 1,500 kilograms. Its engine works at a full power of 20 kilowatts, and there's a constant resistance to motion of 600 newtons. And the first thing we've got to do is to find its acceleration when it is moving at a speed of 10 meters per second. So if we just consider a quick diagram here, we've got 1,500 kilograms. There's a attractive force, which I'll call Ft, which we are looking for. There's a resistance to motion of 600 newtons. Its instantaneous speed at this moment is 10 meters per second, and we are looking for the instantaneous acceleration at this moment. We know that power is this attractive force times the speed. So we know that 20,000 watts of power equals the attractive force Ft times the speed, which is 10 meters per second, which gives us a attractive force of 2,000 newtons at this instance. We know that at this moment the attractive force is 20,000 newtons, so we can apply Newton's second law at this moment on the particle. So we've got attractive force of 2,000 newtons, take away the resistive force of 600 newtons, equals mass 1,500 kilograms times the instantaneous acceleration. So the acceleration is 1400 divided by 1500, or the acceleration is 0.933 meters per second squared at this moment in time. So you can see the diagram there showing the instantaneous situation and the calculations to give us the instantaneous acceleration at that moment. Now we want to find the maximum speed of the car during its journey. So it's worth just thinking about the scenario here. We know that P is the tractive force times the speed. We've been told that the power is constant, and we know that the speed is increasing. Therefore, the tractive force must be decreasing. So V is increasing, and the tractive force is decreasing because the power is constant. Therefore, we must reach an equilibrium situation in which the tractive force is reduced to the resistant force of 600 newtons. At this point, we know that the forces are both 600 newtons, so the acceleration will be 0 meters per second squared, and therefore we will have reached maximum speed. So that's the scenario that we're looking at. So we know that power is tractive force times speed. The power is 20,000. Once we reach this maximum speed and we're in the equilibrium state, the tractive force is 600 newtons and the speed is V. So V is 20,000 over 600. So V is 33.3 meters per second, or if you prefer, 120 kilometers per hour. And again, we can see the method there. Maximum speed means there's no acceleration, which means the net force is 0 and the tractive force is equal to the resistance force. In the next session, we'll be going to be looking at motion on inclined planes.